I will start with recalling the context. So we studied modulus over the ring lambda of power series with coefficients in Zp. And the goal is to provide some algebraic tool to study gamma extensions or Zp extensions of number fields. So let gamma be actually an abelian group isomorphic to Zp. And let gamma n be its unique subgroup of index Pn. And Gn the quotient of gamma by gamma n. So I stated the theorem 6 saying that the completed group algebra of gamma with coefficients in Zp is isomorphic to lambda. And now I will explain a little bit better this isomorphism. So the sketch of a proof. So by construction, Zp gamma is the projective limit of group rings ZpGn, where here the maps are induced by canonical projections. So Gn projects onto Gn minus 1. This induces canonical projections of group algebras, and we take the projective limit here. So in fact, Gn is a cyclic group isomorphic to Z modulo P and Z. So generate gamma 0 of gamma. So this fixes an isomorphism between gamma and Zp such that gamma 0 corresponds to 1. And we can denote by Gn the image of gamma 0 in Gn. So this is gamma 0 modulo gamma n, which is a generator of Gn. And when we have a canonical isomorphism, so canonical up to this fixed data, so between ZpGn and the quotient of ring of polynomials with coefficients in Zp modulo T Pn minus 1. such that, sorry, 1 plus t pn minus 1, so the ideal generated by this polynomial, such that Gn corresponds to T. So this is because 1 plus Tpn is exactly corresponds to the relation, so that Gn at Pn is 1. So I recall that we denote by omega n this power series. And if we use a binomial expansion, so we see immediately that this power series lies in the maximal ideal of varying lambda. So when we pass to projective limits on the both sides, we obtain that Zp gamma is isomorphic to this the projective limit. And because omega n lies in M, so when we take the completion of ZPT with respect to this system of ideals, we obtain the ring ZPT. So this finishes the proof of this isomorphism. Now, using this theorem, one can translate some notation or some objects which appeared in the context of lambda modulus into the language of modulus over gamma. So here, let's start with the following picture. Assume that M is a lambda module. Assume that M is a module over this group algebra. So we can consider M as a lambda module. And so we see that the action of T corresponds plus one here. The action of T corresponds to gamma 0 minus 1. So the polynomial omega nt, which appeared in theorems about lambda modulus, corresponds to, so we should replace 1 plus t by gamma 0, so obtain gamma 0 pn minus 1. So this is gamma n1 minus 1, where gamma n is gamma 0 Pn. It's a generator over gamma n. So omega n of m is exactly gamma n minus 1 acting on m. And m quotient by omega nm is m quotient by gamma n minus 1 m. And we have so-called coinvariance of m, denoted by m gamma n. So the algebraic side of algebraic machinery of Iwasawa theory can be viewed in the first approach like the following picture. So I am really not precise, but I'll try to just explain some general idea. So assume that we have a system Mn such that Mn for each n is a module over ZPGN. Assume also that we have compatible morphisms. So have morphisms for each n, a morphism, say, Pn, compatible with the group structure. So when we can take the projective limit, which will be denoted by m, and so this produces a module over the group, completed group algebra. So we can use, if this module is finitely generated, we can use the structure theorem. So we can use the classification of M up to quasi-isomorphism. So to say something about the structure of M. Now, knowing the structure of M, one can try to come back to this modulus and try to deduce something about Mn. So one can try to descend to Mn and say something about for example, the size of Mn. If we know we have the module M, we can project it on on Mn. So this is a canonical projection of projective limit on a finite level. So here we have some map Pn, P for projection, but this map is not surjective in general. What about the kernel? Pi ends, here I assume nothing. So generally not. Generally not. Yeah. And one can easily see that the kernel contains gamma n minus 1 of M. Just computing the action of gamma n minus 1. So one can say that if we have chance the coinvariants of M, which are by definition exactly the quotients of M by gamma n minus 1, it's exactly Mn. And in this case, we can really recover the size of Mn from classification theory. So in practice, it's not so easy, but one can remark that sometimes, even if this map is not surjective, its cokernel can be bounded. So up to some finite factor, we can again control the size of Mn. And another point of view is that normally such kind of results can be obtained if we work with Galois cohomology. So in a Galois cohomology world, such properties can be proved in a very general context. So I just cite the paper where it was really axiomatized, the paper of Jan Nekovar, Zellmer complexes. So this is a general machinery of so-called Iwasawa descent. Okay, so now we will see an example of such a picture in the situation the classical situation which we started to consider. So we fix a number field F. And a ZP extension of F. And we denote by gamma the Galois group of this extension. Then for each n, we denote by Fn the subfield fixed by gamma n. Sorry?
Can you recall the definition of gamma n?
This is subgroup of index Pn.
So gamma is isomorphic to Zp?
Gamma is isomorphic to Zp by definition. So here the Galois group is Gn. Here this is gamma n. And we denote by Ln the maximal unramified P extension, abelian P extension of Fn. So we denote by Xn its Galois group. We denote by L infinity the union of Ln. So X infinity was defined as the projective limit of Xn. And it is isomorphic to the Galois group of L infinity over F infinity. And the interest of this object was that X infinity by class field theory is canonically isomorphic to the projective limit over P parts of the ideal class groups of Fn. So finally, let denote by G. This is a local notation. It will disappear after the next theorem. Let denote by G the Galois group of L infinity over F. So we have an exact sequence, 0, x infinity, G, and gamma. And we saw the last week that this exact sequence defines an action of gamma on x infinity by conjugation. So gamma acts on x infinity, and therefore x infinity has a structure of lambda module. And again, by functorial properties of reciprocity maps of class field theory, x infinity is isomorphic to A infinity as lambda modules. Now I state, recall the formulation of the last theorem of my.
So this is not a deep thing. It is just definition, playing with definitions. They have the most example models.
Yes. So this is I mean, this follows from the fact that if you consider the reciprocity map, then the action of a Galois group on Adels corresponds to the conjugation here. So it's theorem 7, Iwasawa. Says that firstly x infinite and therefore and A infinite are finitely generated over lambda. Next, that x infinity contains a lambda submodule x tilde infinity such that first there exists some level n0 such that the quotient of x infinity modulo, so I will explain the notation. So we denote by omega n the polynomial omega n divided by t. So this is 1 plus t pn minus 1 divided by t. So that this quotient is finite for all n big enough. So I called this second, and this quotient is exactly xn. So I called this property the control theorem because this allows exactly to descend from the infinite level to the level n, as we'll see. So it relies the infinite object, I mean on the infinite level, the projective limit, to finite levels. Okay, so first let's see how this theorem implies the theorem, Iwasawa theorem about the asymptotic size of ideal class groups. So this theorem implies the asymptotic formula for an of the form p at mu pn plus lambda n plus nu for n big enough, where mu, lambda, nu are some invariants. So the proof is quite easy. First, take first n equal to n0. Then we see that x infinity modulo nu n0 x infinity tilde is finite. Therefore, the size of xn is exactly the product of order of this finite quotient. And the quotient of nu n0 x infinity tilde modulo nu n x infinity tilde. And here we can use our asymptotic formula for the size of a module quotient by nu n. Use asymptotic formulas.
So the first factor is exactly p to the nu.
No, because here also we don't know exactly the structure of this module. We know that up to, I mean, quasi-isomorphism is isomorphic to some canonical direct sum. So nu normally is something which we cannot control. So maybe the point of view is I mean, the naive idea is to determine directly the size of the ideal class group. So it doesn't work. But Iwasawa's approach is to look the asymptotical behavior of this size. So we cannot, in general, prove bound an, so explicitly. But sometimes we can say just that n so can be controlled. Okay. So I will sketch the proof of this theorem. Just say some words.
You determine xn, but is xn and an are the same guys?
Yes, because again it's bilocal class field theory. So the Galois-Grove ramified extension is isomorphic to. Sketch of proof. So this sketch will give something more than this statement. Let's consider the following little bit particular case to simplify. So the first assumption is that only one prime ideal P above the prime P is ramified at f infinity over f. So we proved the last week that if a prime is ramified, it should divide P. So also at least one prime should be ramified. So here we assume that only one is ramified. The second assumption is the following. P is totally ramified at f infinity. So this assumption, in fact, is quite technical. So the condition B can be always achieved replacing the ground field F by some field Fm where M is sufficiently big. I mean that if we consider f infinity over f, so the behavior of this ideal in this extension, so we can have only a finite unramified part, and next it should be widely ramified. So we pass from f to fm just to kill this unramified part. Okay, so let's assume that these two conditions hold. Then, in fact, one can prove two things. The first one is that the commutant of the group G is exactly gamma minus 1 acting on x infinity. Gamma 0 minus 1 acting by x infinity. So we here consider x infinity as a gamma module. So this is T x infinity. the second statement is that xn is the quotient of x infinity by nu n of t x infinity. And if we recall the definition of nu n, this is x infinity quotient by omega n x infinity, and we have the coinvariance of x infinity. So we can take here x infinity tilde equal to t x infinity. So this is really the simplest situation where everything is fine, because the module on a finite level, xn, is exactly the module of coinvariance of the projective limit. So we can recover completely xn from x infinity. So the proof is really very simple, and you can find it in the Washington's books, mainly computations in the group G with some small input of ramification theory, but very minimal.
Wait, I remember that G quotiented by x infinity was this how it's called gamma was this Galois group, yes, gamma whatever. Look at this exact sequence.
Yes, yes.
But if it was already quotiented by x infinity, and this guy is a subgroup of x, gamma 0 minus 1. Is it a subgroup of x infinity? Or it is
Yes, so here is contained x is an x
but it was
infinity.
already quotiented by x infinity, and we got something abelian. How can
Yes.
it happen that the commutator is smaller than this?
I don't.
Because as much as I remember, commutator is the maximal subgroup with abelian, the maximal normal subgroup with abelian quotient.
Yes, it's normal, but we have some abelian because it's not smaller, because you see. So here we have the commutators in some sense. Here we have the commutators of elements of x infinity with elements of gamma. Because
gamma it's
yeah.
This.
Yes,
Yeah.
because minus corresponds to the dividing.
Bigger,
Yeah,
not smaller.
yeah,
So you add something.
yeah. So. Okay, so we have this thing, and
This is true for n large enough?
sorry,
This is true for n large enough, second statement?
this thing, no, it's for all n. Yeah, thank you. For all n.
Only the finiteness is for n.
So in a general statement, n0 cannot be determinate. So this asymptotic formula holds starting from n0. Here we have such a formula which is always valid. But again, if you want to write the order of xn, you cannot say exactly the structure of X infinity. So again, you have sum and 0.
Equality is always.
Yeah. Okay. So, see, in general, I mean, especially if the first assumption doesn't hold. So this is so the first assumption is really serious. So we cannot take X infinity tilde equal to this simple thing. So one should add something which can be written down, but some additional generators. Okay. Here is an example. Assume that f infinity over f satisfies these two assumptions. Assume that A0 is 0. Then an is 0 for all n. So this is something unexpected. So in the easiest case, so for example, if f is q and f infinity is a cyclotomic ZP extension, then for any n, P doesn't divide the P part of the ideal class group of Fn. So P doesn't divide the order of the ideal class group.
If n in this case will be just the group generated by zeta to p to the n, or what?
No, this is something smaller because we cannot take we cannot take the a part primary with prime with p. So really we should extract only ZP extension. So this is generated by yeah. So the proof so consider the module x infinity, so lambda module, finitely generated, and consider the quotient of x infinity modulo m, x infinity. So there m is a maximal ideal of lambda. So as m contains gamma 0 minus 1, so we have the surjective map from this thing to coinvariance of x infinity, which are x0 and which is 0 by assumption. So we assumed that a0 is 0, so x0 is isomorphic to a0, 0. So x infinity modulo mx infinity is 0. And now we use a Nakayama lemma. So it's an example of what can be done using Iwasawa theorem. And, I will finish this part with some remarks. Only few things are known about the invariance lambda and mu. But there are some conjectures. So the first conjecture was proposed by Iwasawa. This is not the Iwasawa main conjecture, it's another conjecture. It says that if f infinity over f is a cyclotomic ZP extension, then mu is 0. So here something is known. So there's a theorem, usually called theorem of Ferrero-Washington. Says that mu is 0 if f over q is abelian. So also the proof can be found in Book of Washington. In fact, there exist several proofs. Another conjecture was proposed by Greenberg. There is something really striking. So, if f is totally real, so assume that all embeddings of f in C are real, then f infinity over f is again cyclotomic, ZP extension. Then both mu and lambda are 0. So this means, this implies, or this is equivalent to the finiteness of the Iwasawa module X infinity. So the example which we studied just before shows that this conjecture holds if the ground field is Q.
The first conjecture.
That's the, yeah. So there is some activity actually around this conjecture of Greenberg, but in fact, it's quite easy to produce examples of fields for which the conjecture is true, but the spirit of conjecture is exactly is different. The spirit should always hold, and existing methods do not allow to attack this process. I mean, this is absolutely transcendental conjecture, like something like. I mean, so the tools. It seems that the tools do not exist still. So if take a break.